In the last lecture, we talked about the Milankovitch theory, which tries to explain how ice ages occur on Earth. Now, when Milankovitch proposed this hypothesis more than 100 years ago, there was no data to verify his hypothesis. He did detailed calculations to determine how much radiation was falling in the northern polar region due to changes in the orbit of the Earth around the Sun. Okay? And he saw there are three major things which change in the Earth's orbit around the Sun. They are the eccentricity of the orbit, which determines how far the Earth is from the Sun. That changes the amount of radiation coming in. Second is the obliquity or the tilt, which determines how much radiation will fall in the polar region. The tilt is more, there is more radiation in the polar region. And finally, there is the factor which determines in which direction the Earth's axis of rotation is pointing. If it is pointing towards the Sun during the summer, then more radiation will fall in the northern polar region in the summer compared to when it is pointing away. So, these three factors play a role. Now, one could test hypothesis 100 years ago, but as we mentioned last class, we have very good data now from Antarctic ice cores and Arctic ice cores, which tell us how much was the ice volume at various times in the past. Now, it is based on a relation between the oxygen 18 isotope that is there in the ice which is deposited in the polar region with the global volume of ice. And the idea is that when the seawater evaporates and deposits snow on the polar region, if there is more and more snow deposited in the polar region, then the ice that is in the polar region will contain less of the lighter isotope, less of the heavier isotope O18. So, when you look at delta O18, which is the departure from some standard, it will go more and more negative. Now, this relationship is very well established. There is no need to even check, because it is merely looking at how the water which was there in the ocean ultimately landed up in the polar region. So, one can relate these two, because as you saw that the amount of ice in the polar region is related to sea level. So, sea level is independently determined in the past by looking at various coastal regions of the world. So, when you look at the sea level variation over the last million years and the ice volume variation from delta O18, they are perfectly correlated, showing that delta O18 is a very good measure of global ice volume. Now, the global ice volume can also be converted to temperature, global mean temperature. So, if you do that and compare the concentration of CO2 in the air bubbles trapped in the ice core with temperature, they are very closely related, okay, on the, of course, time scale of almost a million years. Okay. And so, this was the first time one could see that in addition to the impact of the changes in the orbit of the Earth around the Sun, carbon dioxide would also play some role in the ice age formation and decline, because carbon dioxide is a greenhouse gas, and according to the ice core data, it varies between 180 ppm and around 300 ppm in a regular cycle over the past 800,000 years. Okay. But remember, Milankovitch did not know about the variation of carbon dioxide, so he did not talk about it. So one can think of Milankovitch hypothesis as the trigger, that is the changes in the amount of radiation falling in the polar region due to changes in Earth's sun geometry as a trigger for the ice ages, and carbon dioxide and methane, two of the most important greenhouse gases, would be considered as a feedback. That is, as the temperature increased after ice melting, you would expect CO2 to increase, methane to increase, and when that increase takes place, immediately these two gases will increase the amount of heat it can trap from the Earth's emission. So CO2 and methane will act as a feedback, of course, in addition to water vapor. Water vapor cannot be measured directly from ice cores, but we all know from the Clausius-Clapeyron equation in thermodynamics that as the temperature of the Earth increases, more water will evaporate from the ocean, and hence water vapor will also increase. So you can see that the main trigger for the ice ages, being the changes in the Earth's sun geometry, will be amplified by the increases in carbon dioxide, methane, and water vapor. Okay. Now this is a recapitulation of what is seen from the Vostok ice core. Red is the temperature variation, blue is the carbon dioxide variation, and green is the methane variation. They all go together. They are all closely coupled. Now from this graph, you cannot say whether the carbon dioxide increase in response to temperature increase or vice versa, because the resolution of this data is not good enough to tell us whether temperature lags behind CO2 increase or temperature occurs after CO2 increase. Okay. So this issue will be discussed in a lecture, next lecture, when we have a more accurate data for the last 20,000 years. Okay. Now again, we are repeating here the ice core data for carbon dioxide in blue, okay, and the Dome Fuji data from Antarctica in black, and the amount of radiation falling at 65 degree north during the past 350,000 years. Now you might ask, why am I comparing the temperature of Antarctica, which is on the right scale here, with the radiation falling near the North Pole. Okay. Now this is because according to Milankovitch, the trigger for the ice ages is determined by the northern hemisphere, and he was right, because northern hemisphere is mostly land. It has a very little heat capacity, so small changes in radiation will cause a large change in temperature. Okay. So northern hemisphere will always be more responsive to changes in solar radiation than the southern hemisphere. Southern hemisphere is mostly ocean, okay, except for the big continent of Antarctica was mostly ocean. So southern hemisphere's response to changes in solar radiation will be somewhat muted, will be somewhat slower. So Milankovitch rightly argued that it is the northern hemisphere polar region which is the trigger for the ice ages. And you can see clearly from this graph that the changes in solar radiation in the northern hemisphere, represented by 65 north, summer, July, is quite close to the temperature of Antarctica. Okay. Now, you look at these yellow shaded times when the radiation was high in the northern hemisphere. You can see at that time when the radiation started decreasing from a peak, the temperature also started decreasing from the peak. Okay. So, this is a clear indication that northern hemisphere plays an important role, but you see that it does not happen every time. Every time radiation in the northern hemisphere reaches the peak and starts decreasing, temperature does not automatically decrease here. It decreases somewhat, but for example, in this case, the radiation increase did not correspond to an increase in temperature in Antarctica. So, there are some differences in detail which need to be looked at later. For example, look at this period in the last 100,000 years. The changes in solar radiation in North Pole, they have some correspondence to the peaks of temperature in Antarctica, but they are not perfect. Okay. For example, there is a dip here in the temperature in Antarctica which corresponds to the dip in radiation, but there are many more blips and fluctuations in Antarctica which is not visible in the radiation data. Okay. That means there are more things playing a role other than radiation. We already know that the heat is transported from the southern hemisphere to the northern hemisphere by the Atlantic Meridional Ocean Circulation, AMOC. Okay. That also plays a role. Okay. So, you have to look at both the trigger created by the changes in incoming solar radiation in the northern polar region as well as the heat transported from southern hemisphere to northern hemisphere. Okay. So, what we see is, yes, there is some correspondence between the peaks of the radiation in 65 north in summer with the peaks in the temperature in Antarctica. They are not perfect, but they are quite close. For example, in some cases you can see the peak in Antarctica occurs earlier than the peak in the solar radiation. So, there are some other factors playing a role on account of the ocean transporting heat from Antarctica to the northern hemisphere. Okay. Those are final points which we will discuss later. Now, let us look at how the incoming solar radiation global mean varied during the last million years. You can see its variation is somewhat muted because you are taking a global mean or all latitude and longitudes. So, the variation is not much. I want you to notice that variation hardly, we use a value of 340 watts per meter square as global mean. It has varied between 0.3, 341.3 and 340.9, only 0.6 watts per meter square. This is not much. So, the global mean solar radiation does not vary much, and that cannot be the trigger for the ice age. Okay. So, Milankovitch rightly did not look at global mean radiation, he looked at radiation only at 65 north. Here you can see the annual mean radiation, which shows much more variation than the global mean and varies by around 6 watts a meter squared. Even that is not much. So, annual mean is also at 70 north is not relevant. What is relevant is summer solstice, that is in the month of June at 70 north. Okay. And that shows much more variation, and that variation is between 440 and 580, 140 watts a meter squared. Okay. That is a variation of the order of almost 30%. So, that is why Milankovitch focused on the incoming radiation in the northern hemisphere, in summer, not global mean, not the annual mean at 70 north, but annual mean in June or July. Okay. Now, let us come to a close up of the last 20,000 years, which is very important for us, because that is the last ice age from which we came out, and we saw that around 20,000 years ago, the radiation falling at 6 fair north in the polar region increased from 460 watts a meter squared rapidly to around 525 watts a meter squared, and that triggered the collapse of the last ice age. Okay. So, this large increase of almost 70 or 60 watts a meter squared is what triggered the collapse of ice age. After that, radiation started declining till the present day. Okay. So, during the last 10,000 years, the amount of radiation falling has declined by around 60 watts a meter squared, but this has not caused an increase in amount of ice in the northern hemisphere. So, this shows that the impact of increasing radiation and decreasing radiation is not symmetric. Okay. The system is non-linear. So, the system does not respond in the same way to increase in radiation and decrease in radiation. Now, this is a very important issue to be understood properly, because this is an important factor to understand the onset and collapse of the ice age. Now, to understand that, you must remember that the accumulation of ice in the polar region and its melting is not a symmetric phenomenon. Now, why is that? Remember, when the temperature is very, very low, let us say minus 30 centigrade in the polar region, not much snow will fall, because at very low temperature the amount of water vapor in the air will be very small as per the Clausius-Clapeyron equation. So, if the humidity in the atmosphere is small, that means water vapor amount is small, you cannot have much snowfall. Okay. That is why in Antarctica you hardly get any snowfall these days, because it is very cold compared to Arctic. So, Antarctic is not getting much increase in snow accumulation, because the temperature is too low. But as the temperature increases from minus 30 to minus 20, the ice accumulation starts increasing, and it reaches a peak around minus 5 degrees centigrade. Okay. At minus 5, the humidity is sufficiently high that the snow falling in the polar region will accumulate year after year and increase the ice accumulation. But as soon as you reach minus 10 degrees centigrade, sorry, minus 15 is the maximum, then you come to minus 10, the snowfall starts decreasing and ice melting starts a little bit beyond that. Okay. And once the melting starts, you can see that the melting rate is very rapid. This slope is very much larger than this slope. The slope of ice accumulation is much slower, much less steep than the slope of ice melting. This is a very important factor. That means in the polar region, ice will accumulate very slowly over thousands of years, and then when the temperature goes up and ice starts melting, it will rapidly decline. So, there is an asymmetry between ice accumulation and ice decline, and there is a narrow range of temperature when the ice can accumulate in the polar region. If the temperature goes past minus 10, then now remember this is a mean temperature. So, minus 10 in annual mean would mean much higher temperature in the summer, remember that. Okay. This figure is from a book by Rudiman, which I talked about earlier. Now, let us once more look at the Vostok ice core. The black line is the incoming radiation in the northern region 65 north, and the pink curve here is the temperature as measured from the Vostok ice core through the isotope oxygen 18 abundance. Okay. Now, you can see that in one case there is a very nice correspondence between the peak in solar radiation and the peak in temperature. Okay. So, that is supportive of the Milankovitch hypothesis. Okay. Remember, Milankovitch is saying that when the radiation is highest in the month of July in northern polar region, that is the Arctic, the temperature in the Antarctic is the maximum. Okay. So, he is able to connect the northern hemisphere radiation to the southern hemisphere Antarctic temperature, and that shows the two polar regions are connected both through the ocean heat transport as well as the atmosphere. Okay. The amount of carbon dioxide, methane in the atmosphere is fairly uniform across the world. Okay. If carbon dioxide increases in the northern hemisphere, that increase will also be felt in the southern hemisphere. Okay. So, that is why the two hemispheres are connected both through the atmosphere and through the ocean. But notice that such a nice correspondence you see here about 18,000 years ago is 180,000 years ago is not seen at 100,000 years ago. The temperature peak is much smaller, but the peak is still there. Okay. And if you come here around, I would say 60,000 years ago, the peak does not even match that of the peak in radiation. Okay. But in the last 20,000 years, you see a nice peak in Antarctic temperature corresponding to the highest incoming radiation that occurred around 10,000 years ago. You go back here, yeah, there are some correspondence, but there are also some lack of correspondence. Okay. So, this shows that the problem is somewhat more complicated than what Milankovitch had proposed. Okay. He is right to the zeroth order, that is, he is right that the radiation falling in the northern polar region is the primary driver of the ice ages, but there are more things also happening which need to be accounted for to understand this fact that the temperature peaks are not exactly matching the peaks of the radiation. Now, this can be understood only if we look at the spectra, that is the periodicity of the temperature cycle and the solar cycle. Okay. So, I go back to the energy balance model for our purpose. This balance model is only for polar regions, that is why I do not write S by 4, I already write S. S is radiation falling in the polar region, and this is the 1 minus albedo, this is the amount absorbed in the polar region, this is the amount radiated to space. Okay, very simple model. So, if you for the time being ignore variations of albedo and Olar with time and only examine the incoming radiation and the change in temperature, you would think that these two are linearly connected. So, that the spectra, if you do a Fourier spectra of S of t, that is resolve the Milankovitch solar radiation variation to various cycles, okay, correspond to eccentricity, tilt and precision, the three cycles that you discovered. If you resolve the incoming radiation into 3 cycles, you would expect that the temperature should also show a similar periodic variation, because these two are connected this way. Okay. Now, let us see. Now, this is the power spectrum of the June radiation at 65 north. This is obtained from Milankovitch data, and he shows clearly that the biggest peak occurs around 20,000 years. that is 20,000 years time scale, that is the precession cycle. Okay. The next major peak is the eccentricity peak corresponding to 40,000 year cycle, sorry, obliquity tilt 40,000 year cycle, and there is almost no power at the eccentricity cycle of 100,000 years. So, if you go by Milankovitch hypothesis, you would think that the temperature in Antarctica and Arctic should have dominant periodicities around 40,000 years or 20,000 years, not 100,000 years. Okay. But we already saw that in the last million years, the major power in the variation of ice age temperature was in the 100,000 year cycle. So, straight away we see a paradox. The paradox is that the incoming radiation has maximum power in the 40,000 year cycle and the 20,000 year cycle, while there is no power 100,000 year cycle, but the temperature peak shows the highest power during the last million years at 100,000. This is a puzzle which need to be resolved. Okay. Other thing I want to mention is, in this spectra they are showing 23,000, 21,000 and 19,000, but we are only talking to 20,000 because we want to simplify the analysis, because there are many complexities in the Earth's orbit around the Sun. There are many small periodicities. For simplicity, we are only talking about 100,000, 40,000 and 20,000, but in reality there are many more minor fluctuations. Now, if you compare what is shown in the last slide, which is on the left here, is repeated here, showing the highest peak 22,000, 20,000, 40,000, 100,000, with the spectral power in the temperature data or the oxygen isotope data, it has the highest power at 100,000. The next highest is 40,000. There is hardly any power at 20,000. So, there is a big surprise, because the spectra of the delta O18 and the spectra of incoming solar radiation show different powers at different periodicities. So, this goes against the Milankovitch hypothesis. But I want to remind you that if you look at the data from the archives, Paley-Clement archives, between 1 million years to 5 million years, the peak in the delta O18 curve is at 40,000 years, not 100,000. So, that is what Milankovitch proposed. So, you would argue that Milankovitch hypothesis would work quite well between 1 billion years and 5 million years, because there the peak of the ice age occurs approximately every 40,000 years. But even then we cannot explain why the 100,000 year peak where there is no power still has some power. Okay. But our problem will be to focus on the last million years, where the peak in the temperature or the oxygen isotope abundance is highest at 100,000. Now, I highlight this again. This is the incoming radiation at 65 north in June, and you resolve that into 3 time periods: the 20,000 year time period, the 40,000 year time period and 100,000 year time period. The incoming radiation has hardly any power at 100,000. It has some power at 40,000, 41,000 and a lot of power at 20,000. but the delta O18 curve has the highest power at 100,000 during the last million years, some power at 40,000 and the least power at 20,000. So, when you add this up and get this, these two do not correspond. The incoming radiation curve and the delta O18 abundance do not follow each other. Okay. These two should be similar if Earth system responded linearly to the perturbation caused by the incoming solar radiation. So, this clearly shows that if we want to understand the periodicities of the last million years in the ice ages, for which we have excellent high quality data, we have to invoke some non-linear phenomena, because linear phenomena cannot explain it. There are many non-linearities in the Earth system, and we have to see which of them will help us to understand this. Okay. Again, let me show you the last 4.5 million years of delta O18 from the ocean archive taken from deep ocean cores. They show a dominance of 40,000 year cycle before 1 million years and the domination of 100,000 year cycle during the last million years. Okay. You can see clearly change in the fluctuation of this delta O18. Okay. So, as we got more and more data, the Milankovitch theory does not look so good, but still we all have to agree the basic trigger for the ice ages is the Milankovitch incoming radiation, but after that there are other things going on related to the greenhouse gases, related to the ocean circulation, which trigger changes which alter the Milankovitch hypothesis. Okay. One more look at the difference in the periodicities, which is remarkable data from the ocean ice core, ocean sediments. Now, again I want to highlight this before we go further. We have the summer incoming radiation has a high peak around 20,000, next 40,000, nothing at 100,000. Okay. And you look at the last million years, the major peak in the delta O18 or the ice volume is 100,000, 41,000 little lower. So, these two do not correspond. While in the period between 1 million to 2.7 million, there is some correspondence one can talk about, but not in the last million years. Okay. So, that can only be resolved by invoking a nonlinear model. Milankovitch in his mind had a linear model, and that works quite well for this period, does not work for this period. So, we will continue the discussion in the next lecture. We look for nonlinear phenomena which can explain this paradox. Thank you.